Okay. So, today we're doing. I haven't erased everything yet. Don't look, don't look, don't look. Spoilers. Okay. So, we are talking about right triangles and the centers of different types of triangles. So, I mean, grand overview. Pythagorean theorem is the first thing we're going to talk about. It's only used for right triangles. You've seen it before 100 times. We've done it in my room 100 times before. So, that's not the really main concern, but I just want to make sure we remember it. Now, the centers of triangles is the more interesting part. We have different ways to talk about the different types of centers of certain types of triangles. So if I give you a triangle, depending on the lines that you're given, you're going to end up with different points in the, what would you call it, on the inside of the triangle that are considered the center. And we're going to talk about them later. But first things first, if you have a right triangle like this, we have two things, A and B. We want to talk about those first. Those are called the legs. They help make this 90-degree angle right here. You've got A that comes down and then B that comes over, and that's what's making that 90-degree angle. Those are the legs. Now, the side C is across the triangle on the opposite side of your 90-degree angle. This is called the hypotenuse. Okay, so that's what we need to know in order to talk about the Pythagorean theorem, because in sort of just speech, we would say the Pythagorean theorem is the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse of the right triangle. So, when we're using the Pythagorean theorem, we end up with a squared plus b squared. That's the sum of the squares of the legs. The sum of the squares of the legs of right triangles equals the hypotenuse squared. And we use this on right triangles only. The Pythagorean theorem only works for right triangles. If I give you an equilateral triangle, it's just not going to work. It doesn't work. So let's practice a couple of these. Number one, this 8 inches and this 7 inches make this 90-degree angle. Those are the legs. So your setup is 8 squared plus 7 squared is equal to x squared. And then you just go through and solve for x. So 8 squared is 64, 7 squared is 49, and x squared we don't know anything about, so we have to leave it be. And then we just have to add those values up. And I'm definitely not typing this into a calculator because I'm definitely not tired. There we go. So we have 113 is x squared. Okay, now what? If you're trying to solve a square, you take the square root. Okay? Now, technically, when you take the square root, you have to add a plus or minus, because if you have a negative number and you square it, that would work too, because a negative squared gets you a positive number. But x is an actual physical side length. It exists in this triangle. It's a thing that physically exists. So we don't want to use the negative value. So for now, we're going to ignore the negative value, because while it works mathematically, it doesn't make a whole lot of sense geometrically or in real life. So for now, we're just going to take the square root of 113. So 113, take the square root of that. X is about 11.5. And we're going to leave it like that. Another one, 2 is just like 1. Go ahead and give it a shot. 3, take a look. X is now one of your legs. The setup is the same. You take a leg squared and the other leg squared. The other leg squared is now x. The setup is the same. It's always leg squared plus leg squared is hypotenuse squared. So leg squared plus leg squared is hypotenuse squared. 6 squared is 36. X squared is, x squared. We don't know what x is yet. And 13 squared is, I believe, 169. I am going to double check that. There you go, 169. And then you solve. Subtract this 36. Subtract this 36. Get everything away from that x squared. And then you've got x squared is equal to, 133? and then you take your square root. Again, when you take the square root, you need to make sure there's a plus or minus. In this case, we're not going to use the negative. You can't have a negative side length. It doesn't make sense, at least not yet. So x is just the square root of 133, which is also, bizarrely, 11.5. That can't be right. Did I mess up the first time? The square root of 113. Oh my goodness, the square root of 113 is, sorry guys, 10.6. Oops. That's my fault. I can't press things on a computer, apparently. 4 is just like 3. Okay, give it a shot. Now, number 5. 5 is the same idea. I'll set it up. This is your leg, 12. Your other leg is x. And then your hypotenuse is 20. Your hypotenuse, again, remember, is the side opposite the 90-degree angle. So this is 144. We don't know what x is, so that's going to stay x squared, and that's 400. We subtract 144, so you get x squared is equal to, what would this be, 236, I believe. And then you take your square root. When you take the square root, plus or minus, we're not going to deal with the negatives right now because we have physical side lengths. So x is the square root of 236, which is about 15.36. We'll call it 15.4. Leave it at that. Okay, that's the Pythagorean theorem. You've seen it before. I know you have. I've shown it to you. We've done it before. It's not going anywhere. We're going to do it again and again and again. If you got questions about it, ask now. You can email me all day today, okay? You can email me tonight. I'll answer, I promise. If you've got questions and you don't want to email me, first of all, email me. I don't care. Second of all, you can ask tomorrow if you really don't want to email me. Okay. Now for the interesting part. The centers of triangles, the circumcenter and the incenter. So we've got, now take a look. Just take a look at the picture that we have here. We've got all of these guys right here. Every single one of those is a perpendicular bisector. It's perpendicular and it's cutting this side into two pieces. So the perpendicular bisectors of the sides of a triangle, they all intersect. If you draw out all of the perpendicular bisectors from the sides into the triangle, they all intersect at some point. This point is called the circumcenter. Okay, it's on your reference sheet, that reference sheet I gave you yesterday. This is how we're going to calculate things and figure things out with the circumcenter. So this is the weird part. The circumcenter, this point P, is always equidistant, which means it's the same distance away from the vertices of the triangle. The vertices of the triangle are where the sides of the triangle meet. That would be A, B, and C. So this distance right here, PB right here, is the same distance as A to P and P to C. Those are all the same length. So if we were to mark these 1, 2, 3, 4, we'd have to use 1, 2, 3, 4 and 1, 2, 3, 4. Okay, those are the things that are congruent. The distance from the circumcenter to the vertices. Let's list the perpendicular bisectors now. The perpendicular bisectors would be PD. Remember, those are the guys that are perpendicular and cutting the sides in half. And then we've got PE, and we've got PC. Okay. Well, the circumcenter is where all of those bisectors, those perpendicular bisectors, come in touch and come and intersect each other. So that has to be the point P. So all the congruent segments then, well, I already marked them. The ones that I'm really worried about are the distance from the circumcenter to the vertices. So we've got AP, and we've got BP, and we've got CP, and Technically, we do have more. We have perpendicular bisectors. These are all congruent to each other. We can say that. These are all congruent to each other. And on a different list, we can say BE is congruent to EC because that side, this side of the triangle, BC, is being bisected by your perpendicular bisector. And then we've got AD is congruent to DB for the same reason. And then we've got AF is congruent to, is congruent to FC. Again, because of that perpendicular bisector. Okay. Pause the video, let that sink in, watch it again a couple times. I'm about to go through a couple examples. So, I'm telling you right away, Z is the circumcenter. That means we have perpendicular bisectors. For 1, we have perpendicular bisectors. And 2, we have equidistance from the vertices. That means if Z is in the middle, the circumcenter, this distance right here because it goes out to a vertex, and this distance right here because it goes out to a vertex, and this distance over here because it goes out to a vertex are all the same length. So we want to be able to figure out what that is. Now let's take a look and see what they want us to find first. TU, well, that's this whole length right here. Well, I know that half of it is 19. And why do I know it's a half? Well, Z is the circumcenter, which means this guy right here, this thing coming out of the circumcenter into the side of the triangle, is a perpendicular bisector. That means it's cutting that side in half, which means this guy is also 19. And we have 38 then. I definitely didn't do that on a calculator. So we've got VY then. VY is next. Well, guess what? Z is a circumcenter. A circumcenter is made with perpendicular bisectors, which means we can cut VU in half. Half of 34, I'm not using a calculator, I promise. That's just 17. That one I did all alone, all in my head. Be proud of me, okay? I'm not using a calculator. And now we want to calculate what? UZ? UZ is the distance from the vertex U to the circumcenter Z. Now, the thing about that is, well, it's equidistant to all the other vertices as well. We've got one of those distances already. So we can say, hey, if ZV, this guy right here, is 21, ZU is also 21. This is 21. WV, oh, I see with WV. We are going to have to get a little creative with this. Now take a look. If Z is a circumcenter, let me erase all this other stuff. We don't need this right now. Z is a circumcenter right here. This guy. That means if it's touching the side of the triangle, it is a perpendicular bisector, which means we can have a right triangle, which means we can use Pythagorean theorem. We're looking for WV right here. We don't know what it is. Put an X on it. And then we take the sides 15, X squared. And guess what? Your hypotenuse is 21 because it's across from the 90. And then you're going to solve for X. That's all you're doing. 15 squared is about 225. I'm going to look that one up. I am going to have to double check that one. 15 squared is 225. 21 squared, I can guess, but I got it wrong. It's 441. I was way off. I'm going to subtract 225. Subtract 225. You get X squared is, well, let's see, 441 minus 225. You get about 216. And then you take the square root. Again, when you take the square root, you have to make sure that you are making your answer positive and negative. But we don't need to worry about negatives in this case because you can't have a negative distance. So take your square root. That means X is roughly, it's 14.69. So that would be 14.7. So this length is 14.7. And then TV, oh, well, that's just the whole thing. So we can just take our answer right here and then double it. So we say 14.7, double it. I want the whole thing. That's 29 49.4. The reason we can double it is because this length and this length are congruent to each other. So if I have 1, I just multiply by 2 because I have 2 of the same length. If you wanted to, you could also say 14.7 plus 14.7 if you wanted to. Either way. 2, we have the circumcenter again. H is the circumcenter, and we want to find all of these missing sides. So let's take a look. GD, that's right here. Well, H is a circumcenter, which means that if you have a if you have a segment coming out of the circumcenter and it touches the side of the triangle, it is a perpendicular bisector, which means this whole side is being cut in half. So if you have GD, well, GD is half of the whole length BD. BC, well, if H is a perpendicular bisector, right here, H is a perpendicular bisector, you're going to come out, and that means it's HE is cutting BC, this length right here, in half. So if half of it is 7, the other half is also 7. So the whole length is 14. Now let's see. Let me erase. There we go. Let me erase all this. We have EH. EH is... Oh, are we going to have to do some trickery? Yeah, okay. So this right here is 7. We just found out that that was 7. And we know EH is a perpendicular bisector, which means we have that right angle that I just drew. Now, we want the length of this. Call it X. You have a right triangle. You can use Pythagorean theorem. So 7 squared plus X squared equals 13 squared. That's 49 plus X squared equals 169. That means X squared is, what would that be, 120? X is the square root of 120. That's about 10.95. We're going to call that 11.0. Now, if you're rounding and you end up going into the next ones place, that's fine. You have to write the 0.0. Have to. That's non-negotiable, because if you don't, what I'm assuming is that you think that the square root of 120 is actually legitimately 11, and it's not. The square root of 121 is 11. So we have 11.0. That is just an indicator for me, so that way I know you know that you rounded for that answer. FD is next. FD, are we going to have to do the same thing again? Let me take a look at this. We're going to have to actually get really tricky. We don't know this length, and we don't know this length right here, HD. We don't know either of those. What we do know is this length, HD, is the distance from the circumcenter to the vertex. And we actually have another distance from the circumcenter to the vertex, B to H. So what we're going to do is say, hang on a second. HD right here, this is also 13. This is a perpendicular bisector. I'm going to set up Pythagorean theorem. Now, I'm going to use Y because I've already used X. I'm not really going to freak out about it too much, but technically, since we've already used a variable, we should use a different variable, especially when we're working within the confines of the same problem. So I'm going to draw a wall here, and I've got 3 squared plus Y squared equals 13 squared. This is my leg, this is my leg, this is my hypotenuse. I've got 9 plus Y squared is 169, so Y squared is 160, and Y is the square root of 160, which should be 12 something, 12.6. And there you go, that's your answer. And now if you want CD, well, that's the whole length. That's twice whatever we just found. So 12.6, multiply it by 2, you get about, that's a 1.2, that's a 24, so that's a 25.2. We're good. We're done. Fantastic. Great. Okay. Number 3 is yours. You're given another circumcenter. Now you're going to have to do some trickery. You're going to have to say, oh, look, I've got the perpendicular bisectors. I've got vertices. I've got equidistant vertices. That's the important part. Give it a shot. Let me know if you got questions. Okay. Another one, the incenter. This is a different kind of center. Now we just dealt with a center that's made with perpendicular bisectors, something we learned yesterday. Now we're going to deal with the center that's made with the angle bisectors of a triangle, the thing we also learned yesterday. So the angle bisectors of the angles of a triangle intersect at a point, this point P, it is called the incenter. Now, this time, the incenter is different. The incenter is equidistant from the sides of the triangle. That means this side right here, and this side, and this side. Those distances from the incenter to the sides are all the same. So the angle bisectors, really quick. Actually, hold on. We're learning together. Can I change the size of my, let's go. We're learning. Great. So the angle bisectors are the things that are coming out of the angles of the triangle and bisecting those angles. That's why we have those congruent angle symbols down there. So those are all of our angle bisectors, AP, BP, and CP. The incenter is the intersection of all of those angle bisectors. So the incenter is the point P. And all of your congruent segments is going to be, just PD, EP, and AP. Right there. Those are all, in fact, we can do better than that. Let me go through and erase a couple of these. These are all congruent to each other. So I'm going to go through really quick another one. We've got number 1. P is the incenter. That means we're dealing with angle bisectors. So if I want NP, well, that's the distance from the incenter to the side. And I know that's equal to all of the other distances from the incenter to the side. Oh, look, I've got one right there. That is the distance from the incenter to a side, which means these two lengths are congruent because P is the incenter. That's what it means to be the incenter. So this has to be 8. NK then, I want this length. Oh, my eraser is small. There we go. I want the distance NK. That's over here. Oh boy, how are we going to do this? Oh, you know what? I left something else out. I just realized something. So if we've got NK, that's the thing we want to find. We're going to call that X because we're searching for it. And we know this is 8. We have a right triangle. It's right here. It's right here. But we don't know the length PK. Well, you're right. But what we could do is go back from what we know about your angle bisectors. Your angle bisector, right here, PK. If this is an angle bisector, which it is because we have an incenter, you can say that this length is actually equal to this length. So we have more congruent segments that I wanted to mention, or that I should mention. Up here in the incenter diagram, we also have DB is congruent to BE. We should say that DB is congruent to BE. I completely forgot about that. That's my fault. And then we have EC. EC is congruent to FC. FC, there you go. And then DA is congruent to FA. FA. Oh, well, I did it backwards, but that's okay. Right, and that is the converse of the perpendicular bisector theorem. Or it's actually just the perpendicular bisector. Angle bisector. We're dealing with angle bisectors. Whew, guys, I should not be doing this late at night. I'm usually in bed by now. So, we've got... NK actually isn't too hard to find now. We're searching for NK. Okay, that's 17. Those two things are equal to each other. PK, now I see. We want PK now. Okay. Let's do that. That's our right triangle coming into play. This is 17. This is X. We have our right triangle. This is a leg. This is a leg. This is your hypotenuse. So you have 8 squared plus 17 squared is equal to X squared. That's 64 plus, I don't know what 17 squared is. 17 squared is about 289. And that's X squared. 289 plus 64. is that. Take the square root. X is 18.8. 18.8. And then we want LO after that. Well, same idea. PO is 8 because that's the distance from the side to the incenter. And I've got another right angle right here, right? Because this is a right. Oh, no, I didn't mean to erase. This is a right angle, and this is a line. So they have to have another right angle right next to it. And we're looking for this. Okay. Well, that means we've got 8 squared plus y squared is equal to 13 squared. I'm going to skip a couple steps. Y squared is 13 squared minus 8 squared. So y is the square root of, well, 13 squared is 169. 8 squared is 64. So we've got 105. The square root of 105. What is that? About 10.2. There we go. We are done. Okay. Don't worry about 3. 3 is something I want to talk about in class. But number 2, I want you to give it a shot. Again, let me know if you've got questions. But that does it. That is, what do you call it? That is incenters and circumcenters. Those are the 2 that I'm really trying to focus on. We're going to learn another one called centroid. And that one also is going to be a really important one. Now, if at any point you don't remember what any of these are, you have your reference sheets. Please don't lose it. Use it all the time. I will make sure I also post the reference sheet for those of you that were not here on Monday to pick one up before we, didn't have school today. So I'll make sure everything's in Classroom. Give them a shot. If you have questions, send me an email. Please try them first before you send me an email and say, I don't know how to do it. Give it a shot. Actually try it. But otherwise, that's all I've got. I hope you have a good rest of your day. Hope my class is the only one you're doing a ton of work for. And I will see you on Wednesday. Bye-bye.